Hello, everyone, and welcome to today's today's episode in the series of The Professor Speaks. I am Curtis Busby Earl, and whether you've decided to join us via Zoom, via YouTube, or via UATV, we at the Faculty of Science and Technology here at the UWI Mona are delighted that you decided to spend some time with us this afternoon. For those of you that have or that are joining us for the first time today, the Professor Speaks series is an opportunity for our faculty across all campuses at the rank of full professor to speak on a topic of their choosing. The lectures are typically very informative and engaging with topics that range from the novel to the controversial. Today, we have with us Professor Daniel Kaur. And Professor Kaur will be talking with us about the power of abstraction in computer science and beyond. We're very pleased to have him here today. Professor Kaur is a professor of computer science in the Department of Computing, again here at the UWI Mona. His current research interests are in amorphous computing, robotics and automation, and computer science education. He has taught courses at both the undergraduate and graduate levels, spanning a broad range of areas, including algorithms, theory of computation, language processing, and cryptography. His teaching and research activities have exposed him to a broad cross-section of disciplines, particularly in science, engineering, and education. And he has a keen interest in the problems that exist at the boundaries between these disciplines. He's also a co-inventor of the UWI's cardiac surgery simulator. And that's a computer-controlled device that simulates a patient undergoing open heart surgery and is suitable for training cardiac surgeons in both basic and advanced procedures. Professor Kaur obtained a bachelor's degree in computer science and engineering in 1994, a master's degree in electrical engineering and computer science also in 1994, and a PhD in computer science in 1999, all from the Massachusetts Institute of Technology. He has also received extensive professional training in intellectual property rights management, including IP license negotiations, IP valuation, writing patent claims, and examining patents. He currently serves as chair of the Faculty of Science and Technology's Entrepreneurial Committee and also the chair of the Mona Campus's Entrepreneurial Committee. So I would not like to keep you any further, and I'd like to therefore invite Professor Kaur to take the floor. So Daniel, the floor is yours. Welcome, and thank you so much for joining us today. Daniel, you're still on mute.
Thank you, Curtis. I was waiting for the share screen to pop up so I could get the mute, unmute button available. Good afternoon. Thank you very much for having me. And this afternoon, I'd like to share with you an insight that I have about the power of abstraction, which you will see is something that's fundamental to computer science. I will give a kind of overview from the discipline, and then I will go into some areas of my own research where abstraction has served tremendously. And then I'll talk a little bit about how abstraction can actually be used in everyday life. In fact, we all do it, perhaps, if we don't even appreciate it. I remember a long time ago when I was still an undergraduate, I heard a lecturer at MIT say that computer science is a misnomer for the discipline. And I remember being struck by that. He said, it's neither about computers, nor is it really a science. I never really appreciated what that might have meant until I heard it for the second time when I was a graduate student now, sitting in the same class, but this time as a TA, And of course, now I had more experience and more exposure to the discipline. And after some reflection, I kind of realized this is true. Computer science is actually more about computation. It's how we make it happen. It's how we do it efficiently, how we control the complexity that arises from doing computations. And also we're interested in understanding the scope and limitations of computation. And computation itself is really about manipulating physical representations of information. So in fact, it's quite an abstract concept. And it's not a tangible thing like the computers that I might think of, even though perhaps the computers are in fact our most common mechanism for implementing computation. The first three activities, designing, implementing, concerned with optimality and efficiency, controlling complexity, those are actually activities that are more commonly found in an engineering discipline. And so in fact, that was the basis for that statement. And in fact, it is indeed true. The reason I mentioned that, and I start there though, is that in fact, what this really shows is that abstraction lies at the heart of computer science. And in fact, abstraction, and as I will show you, is really the main tool that we use to carry out mainly these first three activities. Of course, the fourth one as well, but the fourth one puts it very comfortable with the sciences. So I want to share with you, my audience today, just how important abstraction really is. And I would hope that by the time I'm done, you'll see that using abstraction, we can build and control systems with billions of components. In fact, these are the biggest machines that mankind can make in terms of number of components. We can simplify complex problems. It enables us to generalize from special cases. It enables us to think in new ways. And of course, learning interesting techniques in one discipline, especially when they're generalizable and in fact, having undergone the benefit of abstraction, allows us to apply them in other disciplines. And so if I don't cover anything else today, I hope that you'll take away just how important it is, just from these, just even from helping you to learn to think in a different way. Now, let me start by, in a way, illustrating this kind of tower of complexity that computer science is really built upon. The most common representation of computation today is using electric signals, namely voltage, and of course current is another state variable in any circuit. And what we'll do is abstractly say, okay, the voltage at a point, if when we measure it, it's less than some low threshold, we'll call that a 0. If it's above some higher threshold, we'll call that a 1. If it happens to be somewhere in between, we hope that never happens. And we try to design our systems to make sure that we never look at the circuit when a voltage is in between those regions. In fact, it's called the forbidden zone. But what we're doing when you do that is, this is a naming abstraction. We're calling a voltage range, which is in anywhere from, it depends on the family of logic circuits you're dealing with, but it's going to be in a range. And we don't really care what that value is. Once it's within that range, instead of describing voltages within that range, we call it 0. Likewise, instead of talking about voltages above the high threshold, we call it 1. And that's where we get our bits from. Now, one of these bits requires usually some kind of storage device that can save that voltage even for a little bit. That might be a capacitor, might be a transistor. And there are very basic elementary circuits that involve those transistors primarily that enable us to operate on these bits. So for example, there's a very simple circuit called an inverter. And it happens to be configured in such a way that when you put a low voltage on it, one of the voltages within that range I just said, below the low threshold, its output happens to be a voltage in the high voltage range. And so abstractly, what we see or how we regard that is when we put a 0 in, what we get out is a 1. It also happens that when you put in a high voltage, you get out a low. So what we're seeing there is there's a circuit that is capable of doing this transformation on this voltage. We're not interested in how it does it or how those voltages move or when exactly they change. What we do is abstract that away and say, aha, I have a circuit that can convert a 0 to a 1 or a 1 to a 0. And we name that, we call it an inverter. And that's called a procedural abstraction or functional abstraction. And then we can go another level. It's because so far I've only talked about operating on a single bit. If I now take a number of these bits and start putting them together in some kind of coherent, coordinated way, then I can start ascribing meaning to the collection, depending on how I organize them. So the most common example, and this they teach in high school sometimes, the binary representation. In this example on my slide here, I have 4 bits arranged. They're particularly in a particular order. And so, of course, the one on the right is always going to keep its position. And by doing so, we can write out a number, so to speak, in binary. Now, notice that that number is not something known to the hardware, to the computer. The computer, if at the lowest level, they're all just voltages moving around. But we are ascribing meaning to this collection. In this case, when we abstract away a collection of objects and call it something else, regard it as something different from what the constituent parts are, we call that data abstraction. And so you can see where in this case here, 0, 0, 1, 0, well, according to our binary number system, that's what we're calling a 2. We are the ones who organize for those bits to be in that arrangement, and we define the rules for how we interpret what we see. We let the physics take care of the transformations. But at this level, there are operations that we are familiar with, like arithmetic operations, such as addition, for example. And what we have to do is figure out what kind of composition of component parts that were at the bit level, logic gates they're called, can we combine them in a way that provides meaningful transformation to our data abstraction? So once again, we're looking for a composition of these functional pieces into bigger functional pieces, but again, functional abstraction. And then once we can start doing that, at this point, typically we're leaving the hardware. Up until this level, your hardware can take care of all of this. Well, once we can represent numbers, we can repeat the idea. We can repeat the idea of data abstraction. We can take collections of numbers and let them represent different things. So for example, every time you enter your name into a form on a web browser or in any electronic document, you're typing in what we call a string. There is no string at the lowest level, just a collection of numbers. How did we manage that? We arranged for certain numbers to stand for certain characters, symbols. And we arranged for when they appear in memory in a particular sequence, we'll regard that to be the string. Likewise, you can put together bigger and bigger components. So you can put together records with fields containing different types of data, strings for names, numbers for ages, etc. And once you start doing that, we can get even bigger and bigger. At some level, when we're talking about audio or video, and we're trying to produce things like games and simulations and things that we're currently familiar with, your browsers and so on, at that stage, you're manipulating very vast quantities of these bits, typically billions. You're all familiar with, at this point, gigabytes. People can, sometimes some people have access to bandwidth that's transferring gigabits within seconds. And so at this point, you recognize, you can begin to appreciate just the vast numbers of these bits that you're manipulating. And how do we do that as engineers, as the designers of the software that does this? There's no way that we're thinking about these individual bits. At that stage, we're not even thinking about the individual numbers that are making up these component pieces of data that we're manipulating. Rather, what we've done is abstracted all that detail away. And at some level, when it gets high enough, when there's enough data abstraction where we can talk about things like a student record, and somehow that makes sense. Or we can talk about something like a video clip or an audio clip, and that in and of itself presumably makes sense. When we get there, we call that metalinguistic abstraction, because at that point, we're changing the language that we use to talk about our problems and to talk about the solutions that we can implement. At that point, we have now, you can, of course, build higher and higher towers made up of higher levels of meta-linguistic abstraction. For example, at the very lowest level, we have machine language, and that is often, you see, we often use a mnemonic code called assembly to represent that. But nobody codes in that. That's too close to the hardware, too complicated. We build tools that enable us to write programs at a higher level and then compile, that's called, translate it down to that lower level so that the machine can run it. And again, we'll build more tools that will build even more powerful programming languages that enable us to build on top of that. And that, in fact, is how all of computer science is set up. And it's through those abstractions that we're able to investigate, that we're, the limits of computation, that we're able to explore how far we can push the boundaries of what we can do with computers and with computation. So that is how, at a textbook sort of level, abstraction plays a huge role in computer science. Now, what I'm going to do at this point is introduce you to some of the elements of my research and illustrate to you how those lessons from abstraction have played a major role in the kinds of achievements that we've been able to get. And at points, I'm going to illustrate where we're using naming abstractions, data abstractions, functional or procedural abstractions, metalinguistic abstractions. All of them come into play in almost every facet of the kinds of research that I would have encountered. In fact, I'm sure my colleagues also encounter. Now, when I was in graduate school, this is in the 90s, it was clear at that point that parallel processing was running into a difficulty. Parallel computation was tremendously expensive. And at the same time, so to the point where it was no longer economically feasible. Companies that had built parallel processors or parallel machines were losing money fast and going out of business. Paradoxically, though, the cost of building individual nodes was coming down. That's Moore's law, as many of you would have heard of. And so the thought at the time was, if we could build systems made up of many, many nodes, so we get the high level of parallelism, but somehow avoid attempting to connect them in very well understood ways, because that's at the time where the cost seemed to come from in parallel computation. It was the overhead in managing the connection between, if you're trying to scale up to thousands of nodes, it became very complicated to manage the interconnection between those nodes. So the idea that we had in the research group that I was a part of at the time was what was eventually dubbed amorphous computing. And here I'm just going to run through what the sort of major basis of it was. So you have a multitude of nodes all running the same program. That was important because we thought, if you have so many nodes and you don't have a very strong network, you want to be able to have a very easy way to program them all. Each node is not presumed to have any information on its position. That was a conservative assumption that would ensure that no matter how this might have been realized, because appreciate that even though we might think of this as a computational node that we engineered, perhaps there are other metaphors out there, physical systems that could be regarded as a computer, as one of these nodes. So it makes sense to try to minimize what the assumptions are on the capabilities of these nodes. So we presume they had no information on their position, even though certainly more powerful nodes could have GPS, for example. We've presumed that these nodes would communicate only locally, meaning all the neighbors within a particular range. And they all had limited resources and maybe they were faulty. And the question basically was, the research question at the time was, what programming paradigms would be useful to control such a system? You might think at this point that it would be kind of audacious to even imagine that you could. Why, if we have decapitated the system to the point where it seems to just be an unruly mob of processors, why would we even expect to be able to get anything useful out of it? And the inspiration at the time was nature. If you look at, let's take a chicken egg, for example. Once it's been fertilized, all the instructions for forming that chicken are present in that egg. And they're encoded within the DNA as well as the machinery within the cell. And amazingly, after some time, and in fact, with a high, very reliable, rate of reproducibility, that egg turns into a chicken. Somehow, the cells, after they become numerous enough, start specializing. Some become, the thing that eventually produces feathers. Some become eyes. Some become parts of the beak, etc. How does that happen? It's one program controlling all the nodes, because there was only one cell and all the others are generated from that one cell. They're daughter cells, and therefore they have only the same code, which is encoded in the DNA, that the first one had. And yet we get amazing complexity with incredible reliability from such systems. So we thought it's possible. We know it's possible. Whether we can do it is a different question, but that's the challenge. And that was the challenge at the time. Why did we want to do this? At the time, we anticipated that we would see more of such systems. Yes, we could, with some very limited ability, conceive of building these ourselves. But what if you thought differently? What if you thought of bacteria as being potentially programmable entities? Then at that point, you're talking about controlling billions, even, dare I say, trillions of these nodes. But they would be unruly. They would have many of the properties that we presumed to be part of our system. If you could actually build systems that were highly controlled and reliable, as in if you could, come anywhere near the kind of reliability that chicken eggs turning into chickens do, then you could consider doing things like building smart drugs, smart materials. Reconfigurable robots are things that have actually been done since our research took place. Autonomous robotic swarms, again, those are things that have actually been done. Although many of the ones that you would see, for example, when you see swarms of drones performing neat acrobatics, they don't necessarily all conform to all the assumptions here. But certainly at the time, we anticipated that things like autonomous robotic swarms could be deployed in dangerous environments or situations that would be hard for humans or single machines to perform a good job in. Imagine cleaning up an oil spill in a protected environment, or somehow retrieving pollutants from a water source, for example. Those kinds of things are things that you could imagine trying to deploy an autonomous robotic swarm for. And of course, programmable organisms, as I mentioned before, if I have bacteria that I can program to deposit compounds that have particular properties in particular places, I could somehow maybe use them like catalysts. I could construct nanoscale machines with living organisms that I've managed to program. So these were all kind of far-reaching applications, but all of them would have been grounded on top of this concept of amorphous computing. And those were kind of motivating at the time that we looked into it. So here's a problem that I'm going to kind of drill down a little bit into as I share with you. And I'm going to try and keep this at a level that I appreciate it as a public lecture, and therefore I'm going to try and keep this at a level that I think everyone will be able to access. I hope so anyway. So here's a problem I'd like for you to contemplate with me. Assume that all the nodes are stationary, so they're not going to be moving, and each one has the capability to change its color to one of a predetermined set. Question, is it possible to cause those nodes to display a predetermined pattern while respecting amorphous computing constraints? Here's an example. This pattern happens to actually be a real life circuit. If you look at the VLSI design for a chip that's going to use CMOS technology, there actually are color-coded patterns. Each color corresponds to a particular type of material that then corresponds to the kind of process that the silicon is exposed to during the manufacturing process and the etching. So this pattern happens to represent a real-life circuit. In fact, this is an inverter, the very kind of circuit that I was describing earlier. That's actually not terribly important for the exercise that I want us to kind of engage in here. The question is, this is a pattern. This is, for all intents and purposes, just a picture made up of colors white, red, blue, green, yellow. White, red, blue, green, yellow, 5 colors in that case. So the question is, could we design a program or design a methodology for getting an amorphous system to construct, to self-organize a pattern like this one? Remember now, the nodes do not know where they are. There's no central controller or commander. They have no indication of direction, and they only communicate locally by broadcast. I want to give you an analogy that I hope would be helpful here. Imagine this is the pattern that we're trying to construct, and the situation were that you were in a stadium. And you know how normally when you see these patterns emerge from the audience in the stadium, what they've done is place cards on the seat. And at some point in time, they ask everybody, please hold up your card. And then, a camera from above will take a picture and you see this lovely pattern emerge. It might be a flag of something or a sign or some sort. So imagine we had something like that, but now instead of 1 card on your seat, there are 5 in red, green, blue, yellow, and white. And worse, imagine everybody's eyes are closed. You can't even see what color card your neighbor is holding up. So everybody has all 5 cards, and everybody is now asked to hold just one up in such a way that when we take a picture from above, we'll see this pattern. I think you can appreciate that that's not obvious how we would go about doing that. But that's what this question is demanding. We would want a program, a process that everybody will be following. So everybody's going to follow the same process. And we have no central overseer, nobody calling commands from somewhere. Could that be done? That was one of the questions that I actually looked into. In fact, it ended up becoming the basis of my PhD thesis. And the answer was sort of yes. Topologically, yes. Geometrically, meh. It depends. It depends on how densely packed the nodes are and whether they're sufficiently interconnected. Now, let's take a look at how this is going to work. And what I'm going to do is highlight where abstraction came into play. So it started off with an inspiration. We noticed that in biology, chemical signals diffuse to trigger remote reactions, like pheromones, for example. And so the thought was, what if we could model digital pheromones? Then the problem that we're faced with is that each node has exactly the same information at the start. It has no idea where it is, and in every direction looks the same. So for it to think, oh, I'm going to construct this so-called vertical line here, I'm going to be part of the vertical line, it would have to know which direction is vertical, which of its neighbors is part of, if it is part of a line that's going in a particular direction, which of its neighbors will be part of the same line? That's not obvious if every direction looks the same. But the idea here is that with diffusion, if the diffusion could create a difference in concentration around a particular point, then that would be a way to break the symmetry. That was a thought. Here's an illustration of what I mean. So I have these 2 points A and B, and at this point, the neighborhood, everything around them is the same. It's all just white. It's just, there's no no way to distinguish any direction. Let's focus on A for the moment. A has no way to tell which direction is closer to B or further. But now imagine, and that's what I'm showing here, they all look the same. But now imagine that B is somehow able to diffuse a substance. Now, what we'll see is that the concentration of that diffused substance is going to be higher in directions closer to B. And it's lower in the directions that are further from B. And so if A can communicate with all its neighbors, then all it really has to do is communicate, ask all its neighbors, what concentration are you detecting of this stuff that B is putting out? And those that have the higher concentrations are necessarily closer to B. So now we've broken the symmetry. Now we know which direction B lies in. That concept, and of course, once we do that, we could then repeat that process and ultimately form a path back to B. So what we have here is 2 ideas coming together. One, the main one is diffusion could provide a way to break this symmetry. And once I've broken the symmetry, then the idea of selecting a neighbor and repeating the process allows me to construct a path. So I could essentially self-organize a path from A to B if I could arrange for this kind of diffusion to happen. Notice what happened here. We abstracted. We abstracted from well, we haven't even gotten a physical process here, but we were inspired by a physical process. And if we imagine that if we could implement such a process, then that process would carry information. The concentration of the thing, this so-called or virtual pheromone, if you want to call it that, would carry information, namely which direction its source lay in. And that process that we're trying to simulate here would be diffusion. So the idea here is what we recognize is that by viewing concentration as a carrier of information and diffusion as a process that moves that concentration around the space, then we can abstract, the abstraction of it enables us to compute. That was the idea. In this case, a path. But of course, that's just at that point an inspiration and a thought. It still needed to be implemented because notice that in real life, diffusion is a natural process. It's something that occurs, it's part of the physics. It's part of essentially emanating from Pauli's exclusion principle. Matter cannot occupy the same space at the same time. And so it's that's essentially where diffusion is coming from. If I'm in a situation where I'm trying to organize a computation to simulate diffusion, I have a slightly different challenge because now I have to sort of emulate that same physics when maybe I don't have it. Thankfully, though, in this case, I did. Not just me, I mean, it was known. So at this point, small warning, people who may be math phobic might get a little bit frightened. Don't worry, there's nothing made. The bark is worse than the bite. So in mathematics, there's an operator called Laplacian operator. And it's actually used to represent diffusion. Now, the interesting thing here is that the mathematical representation of diffusion is itself going to be a sort of perfect ideal case. And in real life, what really happens when things diffuse don't quite exactly match what's actually going on in our mathematical world. But this operator and understanding, what math can tell us about it, provide very, very good direction to us when we are thinking about physical systems that do have diffusion in them. And so this operator is often used to represent diffusion, that process. What that meant, though, is that for me, in practice, what I needed to do is come up with a computation that could emulate that diffusive process. I didn't have coordinates, as I mentioned to you. The nodes didn't know where they were. So those references to X and Y is not going to be useful to me. Thankfully, though, through the math, we understood that there are equivalent ways of describing that operator. And there are equivalent ways of computing that don't depend on knowing coordinates. And this estimation, which I've written out here, is, and don't worry about trying to understand it if symbols scare you. It basically says, if you have a current estimate of what that concentration is where you are right now, ask all your neighbors what their estimate is and take the difference between what they have and what you have. That's what this term is. Add up all those differences and then scale. You need some number to scale it down by, because you don't want to be changing amounts that by too much. But whatever that sum that you get is and scaled afterwards is how much you should change your estimate by. And if you do that, it will turn out that you'll in some way be simulating that diffusive process. There's a few more important details that go along with that, but that's not terribly important right now. What I'm trying to establish for you is how the diffusive process was implemented and to show that we could achieve it. So here's a little simple setup. We have 4 nodes. P2 has 100 of the stuff, whatever that concentrate, this virtual pheromone we're going to diffuse. So it's essentially the source. P1, P3, and P4 are, and the neighbors is just P1's neighbor, the adjacent nodes are neighbors. So P2 and P4 are not neighbors. And what I'm going to just illustrate as I go through is, okay, so this is what this computation does. So what P2 does is, okay, each node sends out how much they currently have as their estimate. And so, of course, the neighbors receive that. And you can see here, so P2 is receiving 0 from its neighbors. P3 and P1 are receiving 100. That indicates to them that your neighbor P2 has 100 of this stuff. They compute that difference. They take that sum, they scale it. In this case, I'm just using n=10 for simplicity of the arithmetic. And then you use that number, that difference, to modify the value that you had in the first place. So these all started out with 0, 100, 0, 0. Now they computed these differences. And after that update, now it's 10, 80, 10. If you repeat this process over and over, and I mentioned before, there's another piece that we have to talk about, which we won't today, but that has to do with what happens at the edges, the boundaries. But what effectively is happening here, you can imagine, it's like at P2, imagine this stuff is like perfume. If I had a bottle of the stuff at P2 and I take the cup, the stopper off, eventually that the perfume is going to diffuse out. And what you're seeing here, in this case, what's kind of interesting is that I don't have, space is not represented everywhere. Space is only represented where the nodes exist. And what you're seeing is those nodes that are closest to the source got a little bit of that perfume after one step. If we repeat this process again, P4 will get some, but not quite as much as P3 got in that first step. And the amount at P2 will decrease a little bit. And that's kind of what you expect. If you open a little bottle of perfume and leave it in a room, by the time you come back the next day, most of it would have evaporated, if not all of it. And that's that's exactly what diffusion is. Naturally, that's what this digital process was producing. So this is how we had our implementation of diffusion. Notice that abstraction that had come in. In this case, there's a mathematical abstraction or a representation of what's going on physically. We abstracted and estimated that mathematical process, came up with a computation and implemented that, And at this point now, we have a process that could implement diffusion. After that, it was simple to select neighbors that were breaking that symmetry. So remember that picture that I showed you. By implementing the process that I described, this is what happened. You can see the evolution of the pattern. Now, bear in mind, every one of these nodes had exactly the same program. They're all running exactly the same program. They only know anything different by communicating with their neighbors and exchanging that information. In this case, it's diffusion. And based on what is being diffused, they're getting information about what direction the sources of those diffused digital substances are. And just from that information, by putting together the computations that would generate these segments, we could construct that pattern. I've just sort of played out in about 8 frames the self-organized pattern that emerged when that program was run on this ensemble of nodes. You can see the resemblance of what was formed with what was requested. I hope so anyway. So what we see here is diffusion and selection provided a paradigm. And then the careful orchestration of those paths gave us this self-organized inverter. And that's where I was. And at this point, when I showed my supervisor, well, he had actually sort of thrown this out as a challenge. Could we make this kind of pattern self-organized? I'd been working on the idea of that broken symmetry and constructing paths, but I had not sort of composed it in any useful way before that. When faced with the challenge, I wrote a program to then compose those ideas and to specifically construct that pattern. When he saw it, he was shocked. He was like, oh, wow, that's great. I think you can be finished. You need to write up. But before he got there, well, he actually said he was a very excitable fellow, so he got very excited very easily when he saw good things. But he then said to me after a couple of days, you know what you have here is you have a language. At that time, I didn't know what he was talking about. He's like, really, I don't. That's not how I thought of it. But he said, yeah, you have a language here. It's like you have these growing points, he said to me. Yeah. And at the time, I didn't know what a growing point was. But he sort of, said, you can go look it up. But it's like, a plant has a growing point. It has a tip that follows a particular set of sense. It has ability to sense its environment. And depending on what it's sensitive to, it will grow towards or away from. So for example, a very common kind of, that's called a tropism, by the way it grows. A very common kind of tropism that plants exhibit is to grow towards the sun. So he came up with this. When I explained to him how I did this, he sort of retranslated it to me and said, it's kind of like you're sending out these pheromones to create these diffuse fields. You have a tropism that defines how the growing points move through this field of diffused stuff. And as they're moving, they're kind of depositing this color, which is basically just imagining that it's something you're leaving behind. That's a residue of the growth. And when he described it that way, I then went off. I was convinced, I was inspired. At that point, I then went off and basically built an interpreter for this language that we were just sort of making up on the fly. And it was built on top of these processes that I was manually constructing in order to build each pattern. And that's how the growing point language is born. The result of it, this piece of code on the left is actually a small program that would cause a line to grow from A to B. This is the A to B line segment program. It's only about, in fact, it nearly fit on this page. If I had reduced the font, it would have. But I recoded the construction of the inverters within that language, and this is what we got, of course, and that's one run of it. So now the construction of this program, of this inverter, this pattern, is now in my mind as a programmer something I think about in the context of growing points growing towards points in space, and somehow convincing, I don't have to think about what that diffusive process that's ongoing, that ever, that sort of continuous communication between the nodes, constantly asking each other, what is your strength of this field? How much did you just get? And here's my update on comps. None of that is part of what I'm thinking about when we're building this. That's the power of abstraction here. At this level, we don't think about how the diffusion happens. We just know that it does when we ask for it. So in this case, like the command of secrete, if you see a secrete, I just know that a diffusive field is going to get laid down. That 15 was to indicate how many steps it should go. So this language enabled us to think at a different level, a higher level. And with that, we're then able to build more complicated structures. I would never have been able to construct one of these patterns. These are also circuits, by the way. But of course, with the kind of density of nodes, you can see that the geometry looks nothing like a straight line as we would think. But in fact, the definition of straight is actually weird when you have, when your space is broken, or is randomized like this, or sampled this way, I should say. But the point I'm getting at, though, is that the abstraction that was implemented enabled us to do this. So we abstracted a physical process. I regard that as containing information. We abstracted the physics as a computation so that we could simulate the fusion. We abstracted points and segments as conceptual building blocks. And then we applied metalinguistic abstraction to combine those building blocks into the ability to construct even more powerful forms or more complicated forms. So you can see abstraction was rife throughout this research and tremendously valuable in achieving this objective. Now I'm going to move on to something far more practical. So I don't have to spend too much time convincing you that this particular project was had a purpose. And interestingly, because it's applied and therefore well within the discipline, the evidence and places for abstraction are actually almost self-evident, but very valuable nonetheless. So the UE cardiac surgery simulator is a tool for training cardiac surgeons. It's like a flight simulator. It's for cardiac surgeons what a flight simulator is for pilots. The picture on the right shows you what the simulator looks like, the top picture, and that's actually Dr. Ramphal, who's the co-inventor. It's actually his brainchild, and he recruited me onto the team. But this is what it looks like when it's set up. So this is what a patient would look like when they're prepared for the operating room, just before they would undergo open heart surgery. In this particular setup, these two individuals who are closest to Dr. Ramphal were the trainees, and they're about to get some lessons on the simulator on how to perform a particular procedure. These two other individuals next to them were in fact trainers, but in a real operating room, they would be like a scrub nurse or something. Like the person standing in that position would be a scrub nurse. So in this particular setup, it sort of replicates what the operating room setup is like, and really is quite realistic, at least from the team perspective, in terms of where people are standing and what they're doing. But to get back to what it is, this, you can't see where the heart is, that's called a pericardium, very well. And so this is kind of a blow up. It's not exactly the same picture, but you can see here that this is the heart inside the pericardium. This is what it looks like up close. That heart is a pig's heart, and it's a real pig's heart, so it's real tissue, but it's placed in a mock chest cavity. And in fact, that was what was different about it at the time. The fact that it's a combination of physical tissue and electronics and mechanical components. Balloons are inserted into the heart, and those balloons are inflated and deflated by a pneumatic pump that's controlled by a computer. The computer also controls an electronic display of vital sign traces which are supposed to represent what that patient would be undergoing, the simulated patient. And of course, because we have a computer controlling a pump, we can provide any kind of beating rhythm that is within the capability of that pump. It also means that we could set up any kind of condition that a patient might be undergoing. This is a simulated patient. And we can then, therefore, we can arrange for crises and emergencies to arise when a resident is being trained. And of course, so the computer is really responsible for two things here as the display is, as it regards the display. One is to make sure that the way the heart is moving is in fact in sync with the ECG trace that's on the screen. And of course, making sure that the rest of the waveforms look realistic for the particular condition that's supposed to be simulated. So these are the components of the simulator. And those are all the parts of it. Now, what I'll do here is show you the simulator in action. And what you're about to see is a resident being trained on a very simple process. I shouldn't say simple, a very essential process that's a part of every open heart, almost every procedure, which is it's called cannulation. And basically, it's just a first step of putting the patient on that heart-lung machine, which is going to do the pumping of the blood into the body while the surgeons operate on the heart. Very often, they want to stop the heart so that they can operate on it, whatever they have to do. And obviously, if the heart is not beating, the patient is going to die on the table unless there's another means of pumping blood through the body. So that process, there's a machine that does that, and the process of getting the patient onto that involves this first step called cannulation. And it involves, there's a little device that is where the interface is going to occur between the tubes to the machine and the vein or artery of the patient. Now, the video I'm going to show you is a clip of a student, a resident, attempting to insert that cannula into the vessel. In this case, I think it was the aorta. And he is having a great deal of difficulty. In fact, at this point, I'll show you and then I'll talk, because I understand you won't be able to hear the audio in it. I'll tell you what the exchanges are, and then you'll begin to see, I hope, the value of the simulator in that context. Just a little warning, those of you who might be squeamish, if you see, everything here is simulated, so it's not real blood, but it looks real. And if that will bother you, then perhaps you might want to turn away for the video clip. So here is the heart beating. And the fluid flowing through it at this point is simulating what the real blood in a patient would be like. You can see it's under pressure because you can actually see that the blood spurts out when they put their finger on it. At this point, he's already cut the hole in the aorta. He's supposed to be putting that cannula in. You can't hear it, but this person on trying to put it in as a student, the person opposite him is the instructor. And he's very patiently giving him instructions on how to do it. The student is trying to put it, it's not going in. And you see, he's showing him the motion, said, do it like this. And he's pausing to explain to him a technique for inserting the cannula into the aorta. And here the student is trying, and I mean, this video is going to end before he actually succeeds, but he eventually gets it. In fact, right now, the instructor is telling him, look, if this ever happens in real life, you need to call your attending surgeon to come and help you. Don't keep doing this over and over. Now, remember where we're at. Without the heart simulator, at this point, residents learn to do cardiac surgery in some other way. Maybe on a pig, maybe on a stationary pig heart in a bowl, and in fact, in the operating room as well. Now, of course, if this had been a real operating theater, that attending surgeon would never have been, it would never been okay with that resident trying over and over and over again. But what you saw here was that resident was allowed to make those mistakes while he was learning on the simulator. And eventually he did get it in. And so now that resident has a feel for how it feels when that cannula goes in, while the heart is moving, while the aorta is under pressure, which are not quite things that you could get if it were stationary in just a dead pig's heart in a bowl, or if even a cadaver, right? You could get it with a live pig, but one of the things that you'll have with a live pig is maybe the pig might go into cardiac arrest. The pig, when on the operating table, may end up having all kinds of other complications that were not part of the lesson plan of that day. So when you look at what the possibilities were, what was available to train cardiac surgeons, you really had 4 options. It's pig heart in a bowl, cadaver, and those have high control because you can, since you have total control over the scenario, you can set up anything that they can provide. But they're not very realistic when you're trying to simulate a live action patient. Of course, a live patient is perhaps the highest fidelity that you could get, but you really don't have a lot of control. You can't just induce a condition in a patient just so that your resident can get training. That's not okay. And a live pig, similarly, you might be able to do that to a pig. You might be able to put it under certain conditions. But typically what you're doing with a live pig is trying to expose your residents to what that experience would be like in a real operating room. And I've seen examples at symposia where the pig just sort of died on the table, and that was not part of the plan, and the lesson had to be cut short at that point. The UE cardiac surgery simulator provided a 5th way. It was a device that had the kind of control that you could execute with a pig heart in a bowl or cadaver, but the fidelity of what live pig could have offered you. And so it was sort of this sweet spot of ability in this space of control versus fidelity that wasn't available before. And that was the true contribution of the UE cardiac surgery simulator to the discipline. So some of the things that came out of that is the first patent that was licensed by UE. It set the bar for cardiac surgery simulators. Many other simulators started comparing themselves to our simulator. It inspired other hybrid simulators. These are simulators that used animated tissue to simulate whatever the condition of the patient for the particular kind of doctor they're trying to train. And it actually did influence the standards that are being set for cardiac surgery training. And as a consequence of that, it has affected the way training in the US is currently done. And we expect once it happens in the US, then, we have seen residents and doctors from other countries ask about the simulator. In fact, in some cases, even get an opportunity to do a training session or so on with it. And they're not in the US. But the point is that you can see that once the US takes a step in a particular direction, then they have a lot of influence. So in fact, the fact that we've been able to have an influence on how cardiac surgery training happens in the US also means that it's the potential is there for it to happen in the rest of the world as well. So here's a little bit of the backstory, and then I'll get to how the abstractions come in. This, as I said before, it was really invented by Dr. Paul Ramphal. He's a cardiac surgeon, but inventor extraordinary because he's a very creative individual and he's very hands-on type of guy. And so he actually made the initial prototype, and it was completely mechanical. He wanted, of course, for it to be able to be correlated with display on the screen and for the control, the beating rate and so on to be controllable. And so he recruited myself and Michael Craven, who was at UTech at the time, to help him do this. And we did that. And by 2004, we had a working type that he was using with his residents until about 2007 when he left UE. Coincidentally, out of the blue, we were contacted by the chairman at the time of the American Board of Thoracic Surgeons, Dr. Richard Fines, who was at the time had just moved to University of North Carolina, and had come across the simulator online, a video of it, and wanted to know if this was real. Could he see it? Could he inquire about how he could get one, use it, etc. Long story short, we ended up going up to UNC and reconstructing the simulator at UNC. And he took it on the road and showed it around to various symposia. And it was used to train, attendees at those symposia. It was shown at conferences, and it created quite a buzz. And so by 2010, we had enough interest that we designed this program where we would put one of these simulators in 8 different centers around the US. These are very prominent institutions. Harvard was involved, Johns Hopkins, Mayo Clinic. I shouldn't have started because I have to finish. I'm going to leave out important people. Strong Memorial, that's Rochester, University of Washington, Stanford, Vanderbilt. So there were 8 of these centers that were participating in the study. Each of them got a simulator. Of course, at this point, for them to get one of these, bear in mind that the prototype that we first built required both Paul and myself to set it up. And so when it went on the road, every time, that was Paul and myself having to make a trip to the US in order to help make the simulator move from one place to the next. Obviously, that's no kind of machine to be sending out to these 8 institutions for them to be conducting their studies on curriculum design for this discipline. So what we ended up doing was redesigning a new prototype that consolidated all the pieces, put them into sort of one compact package, and then was delivered to each of these institutions as separate, 8 sort of more consolidated machines. At that point, that was just me. That was done right here at UWI with myself and my graduate student and a few undergrads at the time. Paul is remote, not in Jamaica anymore. So he would provide the design of how the thing was configured, but all the engineering of whether the kind of pumps were spec'd at the right level and whether the amount of energy being delivered was appropriate and whether we had, made our wires fat enough to carry the current necessary. That kind of engineering was what I had to deal with. Anyway, we did that. And then we had the successful commercialization in 2013. The pilot study with those 8 institutions wrapped up in around 2014-15, and it produced a curriculum for simulation-based cardiac surgical training. And our simulator is at the heart of that program, no pun intended. It wasn't the only simulator used, but it was sort of the one that was, took up about maybe 40% of the time allocated to training. Now, I did promise to be talking about abstraction. At one level, the entire system of that simulator is an abstraction. It's an abstraction of the operating room with a heart patient on the table. And so obviously that one is sort of obvious. But there are a couple of places where the discipline of applying abstraction, looking for it, came in really handy. In the first instance, when I was trying to work with Paul on developing the ability for the computer to produce all the kind of range of modes that he needed, I didn't know very much about heart surgery. In fact, I knew very little biology. I didn't even know the anatomy of the heart at the time. But what he would need was a range of possible behaviors that the patient could, the simulated patient could demonstrate or reflect. And what I ended up having to do was sort of abstract away all those conditions, the full space of conditions, and sort of reduced it to the things that could be observed. So that was an example of how I used my discipline to help me understand another discipline. In this case, it was an interface between our 2 disciplines. And in that way, I was able to develop the code in such a way that even when I didn't know what conditions would be demanded by Dr. Rampal, whatever he needed at the time would be available, because what I did was essentially build a system that could deliver anything that could be requested once it was expressed in terms of the beating mode and the combination of vital signs that would be seen on the screen. So that's an example of a kind of procedural abstraction, naming abstraction as well, that I used in order to be able to interact and interoperate with somebody from a different discipline in a way that we could make progress. There's another nice episode where that discipline of applying that abstraction came in really, really useful. The hydraulic modes, which are the states that control where the fluid is going at a particular point in time, were all very specifically designed and defined, I should say. Paul was the one who gave them to me, Dr. Ramphal, so to say, okay, these are all the different modes that we will have to make fluid flow through this, the mannequin and the heart in. And so you need to just make sure that every one of these can be achieved. And that, you know, that's what he would do manually before we built version 2. When I looked at what was required, there might have been about 6 different modes. Instead of actually implementing those 6 specific modes, what I did instead was recognize the constituents of those modes. So this is a sort of recognizing those as special cases of a more abstract and general description of such a thing called a configuration of pumps and valves. And then each of the ones that were specifically asked for, I could then provide by sequencing the constituent components. So what I did was essentially build a tiny language, metalinguistic abstraction in use, to be able to specify a combination of these configurations that would lead to what Dr. Ramphal understood as a hydraulic mode. Now here's where it came in really handy. So obviously, when it just got deployed, he got what he was expecting, and he's not aware that there's this metalinguistic abstraction there underneath. But after one of these symposia one day, Dr. Fine said to him, you know, the simulator has a problem because during cannulation, there's supposed to be blood in the heart. And what was happening during this particular session, he noticed, is that the heart was empty. So when they put the cannula in, blood is supposed to be coming up it, and they're supposed to actually be able to observe it and see, you know, it's supposed to be like an indication of the pressure changing. And so as the heart is beating, you can see the fluid levels rising and falling inside of that, the cannula. And he said, it's not there. And that's not very realistic, you know. And I remember that there was a bit of a kind of a slump in Dr. Ramphal's response to that. And he was like, what? You know, he was like, how did that happen? And then as I sort of worked out how come that had come up, they were trying to figure out how they're going to fix that now. Because at this point, the simulators, not all of them had been delivered, but some of them had. And at this point, it had been, you know, pretty much built. There's no going back and changing that. So at this point, I'm listening in most of the times when they're talking about the particular issues and opportunities that may arise within the medical simulation field. It was kind of above my head, you know, not something that I was very well equipped to fully participate in. But in this particular case, because what I heard them talk about was definitely something that I had to contemplate myself, because of course, the simulator itself is well within my purview. So they're talking about the issue with the simulator. I recognized that what they needed was a mode that didn't exist yet. And when I looked at what the capabilities were, it turned out that it was actually possible to configure them, and to configure them in such a way that it would deliver the desired outcome, namely blood would be in the heart when they were doing cannulation. And the beauty of that is that it turned out, in order for me to implement that, I did not have to pull up any hardware. We did not have to reconfigure tubing. We did not have to change any wiring to pumps or valves. None of that. It was, I went into a file, I changed the configuration in that file, restarted, and it was there. Of course, the response of both Dr. Ramphal and Dr. Fines at the time was, when I said I can do this, they were very, very nervous and hesitant because they thought I'd have to go into the machine and start pulling it up. And they're like, no, let's find another way. I said, no, that's not necessary. It's all software. And so, of course, we were able to do that. And from there on, we had that as an extra mode. that was the one to be used when somebody's learning to cannulate. But as a nice little episode I'm describing where the principle of abstraction was applied in the implementation of the machine and provided a mechanism later for a potentially disaster situation. So that is the full story of how abstraction has played a role in these technical ways. Now, I just have a few more examples outside of the discipline, and you might think that they might be slightly trite, but I hope at this point that even if you sort of want to, debate the out of discipline examples that I might raise, I hope that if you've understood enough of what I've talked about today of how abstraction has played a role within the discipline, that you might be yourself inspired, or your eyes may have been opened to ways that you probably have been using abstraction all along, and perhaps maybe you weren't explicitly aware. And I hope that with that, you're going to be able now to be able to sort of think more deliberately about how you go about solving problems in your day-to-day life coming up in the future. So here's one, abstraction in legal agreements, right? This happened recently. So an external company entered into an agreement with UWI, and they had a particular expert as a UWI member of staff that they wanted to engage specifically for their services. So they wrote into that agreement that they wanted to be able to co-opt that time, and they would compensate UWI for the time of that individual. I saw that because of the current role that I play as the chair for the entrepreneurial committee on the campus. I was part of that negotiation. I saw that and I said, there's an abstraction here. This company sees this expert because of the match between their discipline and the reputation that they are aware of. But I saw this as, in general, this company could potentially be interested in engaging services of anybody else on campus that would be relevant to what they do. And for that matter, maybe any other company in the future engaging with UWI might have a similar kind of interest. So if we're going to think about, rather than making a special case for how we would, build the company and sort of figure out what they ought to compensate the university for, why not make this generic? Why not make this a process that we could use for anybody else? And that's exactly what I did. So it's not finished, but that's the approach that we've taken. And now we will have an instrument that will be available for any external entity when once they have a signed agreement with you, of course. If this kind of engagement is something that they're interested in, we would have an instrument and a process to readily address that and handle that. And that came out of just thinking in this way that I've described, looking for those abstractions to generalize, looking for those abstractions to simplify perhaps complicated scenarios. And this last one, I thank my wife for giving me this one because, and I think it's a very valid example. But here's one. So when our children are much younger, my wife read a lot of books on parenting, and there was one piece of advice that she came across about appreciating the difference between principle and preference. When you have a position on something, you're trying to get your child to do something a particular way, and they don't want to, or they're doing it somehow differently. The advice was, is that difference because of a principle you hold there, or is it because of a preference? And if it's a preference, then perhaps you ought to think about giving some leeway to that child to express themselves in a different way. And I think that this is a very useful example of an abstraction, because what we're saying here is really principle and preference are two orthogonal components responsible for the beliefs that we hold on to. And so if when you now end up in a kind of strong altercation or potential altercation with a toddler, or maybe not toddler, maybe a teenager, you could sort of query yourself, why are you so opposed why is there so much tension or friction in this particular situation? Is the basis of that about your principle, or is it about your preference? And if you can think that way, then that means you can moderate the resistance that you provide to only be proportional to the component that's responsible, that's for the principle. And that kind of thinking, I think, enables us to reach that position of agreeing to disagree and sort of, reach a harmonic position in our relationships with those that are near and dear to us. I like that example, and I'm sure you all probably can find other examples. But at this point, I've already gone, I think, over my time. So I will pause here and take questions. Oh, so right. Don't compromise your principles, but be tolerant of preferences that might be different from your own. That's a takeaway lesson if you apply abstraction in that context. But I thank you very much. Thank you very much. And just before I close, I just want to very briefly, very quickly, acknowledge, of course, family and friends who would have encouraged me when I was younger and in high school. I know some of you might be even watching now. I'm not going to start calling names because that list is very long. But there are some who, without whom I would never have had, as a child, the kind of confidence that I did and curiosity, and to have been encouraged in the ways that I did eventually get to MIT. And once I was at MIT, I had some wonderful friends there who made that experience a wonderful thing. And then later on in graduate school, I had wonderful supervisors, Jerry Sussman, Hal Abelson, who really helped to see the forest from the trees, helped me to see that. And then the Swiss group that we were part of was this amazing group of very talented individuals. And that's really where I learned a lot of the skills that I have for coding and understanding how systems work. And then, of course, the eukaryotic simulator would never have happened without Paul. And I would never have been a part of that project had he sort of deliberately went out of his way to come find me and recruit me. He told me later on. I wanted to call out Matthew Budram specifically. He was a graduate student of mine who was my sort of partner in crime while we were building the 8 units that were sent out. And these undergrads, Marcel Blair, Raymond Dixon, were also very instrumental and helpful in the development of that project. So that project would never have succeeded without these individuals, and it would be remiss of me not to have mentioned them. Thank you very much for your attention. Apologies for a little bit over time, but I'd be very happy to entertain any questions and discussions at this point in time.
Thank you very much, Daniel. That was very, very interesting and informative. And I must say, I don't want to, I can't express, I think, quite accurately how important that work was, in particular the cardiac surgery simulator. And I say that because, there are quite a number of reasons. One is it seemed to be, for example, the definition of interdisciplinary collaborative research. There is computer science involved, there is physics, there was medicine, there was chemistry. And if memory serves me correctly, I remember you and Matthew and others, when you were building and at the point where things were also being improved upon, there was a 3D printer, and you guys were also printing some of the components. So that also spawned other sub-disciplines in computing, which at the time were somewhat nascent. So it really has been very interesting. I wonder, you had mentioned that in the States, there were about 8 institutions. Has that number grown? 1. And 2, I was also wondering, after the creation of the curriculum and having implemented and installed the simulator at a number of these institutions and locations, was there any study that was conducted that could tell us what the impact of introducing those simulators has been in terms of the success of the curriculum coupled with the simulator in the students that were being produced as a result?
Okay, so you asked a number of questions. Let me just try and take them one at a time. So in terms of other institutions using them, there are a few. I am actually not fully aware of which ones have bought simulators and which ones haven't. Once we licensed the right to manufacture and sell, then the sales part of it is handled by the company. You would get, a royalty return from that, but that's, so I'm not necessarily kept abreast, but I am aware, just because up until the time when I was still going up regularly to participate in an annual event that they had called a boot camp, I am aware of at least 3 other commercials having been sold to participants, to institutions that were not participants in the initial 8. You have to bear in mind that those units that we built and sent up to them, those are never intended to be long-term use. There were prototypes that were developed for that study. They would have us as accessible to service and fix and troubleshoot, because they were proofs of concept, really. I mean, that's what you can expect to build within a university context. That's why you license a company that can sort of provide a kind of service support and proper, commercial support for it. So that also comes with a little bit of distancing with things like how much sales have happened and who else is using it. So I actually don't particularly know, but I am aware, for example, one of the members, in fact, the person, Dr. Muckadam, who was at University of Washington at the time, I forget where I want to say Ohio, but let me not say it wrong. He's no longer at University of Washington, he's moved somewhere else, but he got a commercial version and he's using it to sort of, he's now sort of at the avant-garde of cardiac surgery training, and people go there so that they can get to, I mean, I shouldn't say that that's the only reason they go there, but that's certainly one of the highlights of that program that they have there, that it is heavily influenced by this curriculum that they came up with. In terms of, I think you're asking whether there's evidence that the products of the simulator turn out to be better.
Yes.
Is that?
Yes, basically, if there has been any research or studies.
And so at the time when we were doing it, that's certainly one of the directions that we wanted to look at. But I was sort of a pride, because of course, coming from my discipline, I was asking those questions. Why can't we set up some kind of assessment mechanism to compare? And I said, no, you can't do that. So there are a couple of things. There are some sensibility issues about trying to because already there are differences between institutions in how they might do things. And so there are some things that are preferences as opposed to principles, even in terms of a discipline like cardiac surgery training. And so that's one element of the difficulty of comparing. The other one was an ethical one. If you are, how are you going to compare? If you compare on the simulator, then you don't know if you just pre-biased the people who were trained on the simulator because they're not more familiar with the simulator. Or maybe the simulator is not even a lifelike good enough representation of what's really real. So it's not even necessarily meaningful if you train and test on a simulator and then give it turns out that those who are using it more than those who weren't get better scores because you have confounding variables there. And so then that means that now you're going to have to do the comparison with real patients, people, so what is then at that point the means by which you're going to do that evaluation? And you can see how you're going to run into this ethical problem. That's not to say that it's not been done. I don't know, to be honest with you, where it's at this point. I do know that that was a challenge at the time that we were contemplating it. One thing that was very clear, though, that the simulator has now provided, 2 things really, that the simulator has provided the ability for. One is that it exposes residents to the problem, or not problem so much, but the experience of being in charge of the operating room. That is not something that they would ever get to do when they are residents.
Yeah.
So what that meant is that in real life, having been trained on real patients in a OR, always under tutelage of the attending surgeon, the very first time that they are in charge is after they've graduated, and now they're in another room somewhere else on their own, in charge for the first time. And what this simulator enables us to do is essentially allow them to be in charge, allow them to flop around and sort of forget what they're supposed to do, forget the instructions they're supposed to give, and make them have to recall them, make them have to give those instructions at the right time. Because some of those instructions, there are lots of things that are on the direction of the surgeon. The surgeon has to make sure, like for example, before you go on that heart-lung pump machine I mentioned, you have to make sure you give the patient heparin. That's a blood thinner. Otherwise, the blood is going to get clotted up and the patient will die. So it's an example of, and it's not even like the doctor himself has to actually give the heparin. It's the anesthesiologist who's going to do it, but the doctor has to order it, has to say, was it done? And there's an important part of it that he actually says, give it now. And at some point you ask, what's it like? What's the status? Those are things that when they're in a simulated environment, it's just like pig's heart in a bowl. They're not worried about that, right? But they're real and important. So that's one thing that the simulator, everybody agrees, has done. The other thing that everybody has agreed, when I say everybody who was participating in the study and others that we spoke to, is that you can use the simulator to train residents on conditions and scenarios that are rare or highly unlikely, but deadly. So you can have crisis scenarios that if that were to happen on a real operating table, chances are high that the patient will die if that doctor doesn't have the experience of knowing what's supposed to be done in that exact situation. Now, the thing is that those are things that are also covered in textbooks, but because they're so rare, then many times a resident may go through the entire program. Yes, they're going to the OR. Yes, they're participating. They're hands-on. They're getting that exposure. But because they're so rare, they may never have seen it in real life. So the only knowledge they would have had is the textbook description of what to do. And with the simulator, we can arrange for that condition to arise. We can actually plan a lesson, so you can have in fact, that was one of the modules of the program where they sort of identified 2 or 3 different crisis situations for which the approach, the procedure was well documented, well understood, and they would arrange for that to happen. Of course, they would do it in a way that the resident wouldn't necessarily realize at that time that's what was happening, but at least the instructor could make it be a part of the program. And therefore, by the time the resident graduates, they have a certain, even if it's only in the simulated environment, at least that resident would have had that muscle memory at the very least of what was happening at the time. Because sometimes it really is a matter of few minutes and seconds that can make the difference.
Well, I must say that given the fact that, at least in the States, the collective term heart disease is the #1 cause of death, it certainly must still, we could assume, will eventually have an impact on maybe those numbers in years to come. But I also have, and this is another question, and it's arising from the main theme of your talk, and it's abstraction. I know as well as computing is my area of research, and so generally speaking. But the idea of abstraction, as you've talked about it, seems to be almost fundamental. It's ingrained in almost everything we do. And that was also brought out in your examples, that you could apply abstraction to relationships, you could apply abstraction to creating legal documents, and so. And it begs the question, and as we said when we first started, based on your years of teaching and so, is abstraction something that can be taught? Is that process, is it something that is ingrained in all of us, or is it something that has to be taught? Is it something that has to be coerced or nurtured to come to sort of fruition in all of our modes of thought and in our interactions? What do you think?
Yeah, and answer that is yes to all, right? It can be taught to the extent that I can show you examples of good practices. I can show you examples of these concepts in use. So I can tell you, this voltage, we're going to decide that this low voltage is a 0, and when it's high, it's a 1. That's a naming abstraction, for example. And thereafter, you say, well, what's the value of that? And you say, well, notice that we're no longer talking about actual voltages anymore. We're talking about zeros and ones. And once I'm talking about zeros and ones, I can then start talking about binary numbers and then numbers and so on. So the conversation, the things you're focused on, where your attention is, has changed, and what you then are able to think about beyond has improved. So you can expose your students and individuals to the good practices, but can you get them to be good at applying it? Right. I don't think that that's something that you can. I don't know that we know as humankind how to do that. The way that we teach those things in engineering schools, in engineering programs, in computer science, we actually do it by using lots and lots of examples, and giving students an opportunity to engage by giving them problem sets that would require, if done properly, the application of those principles. And it's through the practice that we're trying to induce into them that we're hoping the transfer of that skill, of applying it in their everyday, well, not just everyday world, but in this case, in the professional world, that we're hoping that that takes hold. And I don't know that we have any better method yet. Maybe one day when we can measure the brain, then maybe.
Okay. Well, I'm going to pose a few questions to you from the members of our audience. And the first, it seems, is coming from someone who does have an appreciation for abstraction as you defined it and as you were discussing. And the question is, in games, how do we actually apply physics to creating that sort of realism in games as we see them today? So the example that was specifically used is in FIFA or NBA, where the ball will only move when it is either kicked or touched or it comes into contact virtually with the avatar. How do you think, or how was abstraction employed or used in that scenario?
So those games, especially in today's with today's technologies, are really high fidelity simulations of physics and mechanics, really. And if you think about it, what is required, so very similar to what I had to do when I was simulating diffusion. When you think about a computational environment, you get to implement your own physics. That's a kind of profound thing if you think about it. You get to say what can happen in this world. So if I want to create a world, which is what a video game is, that is going to resemble the real world, then what I'm going to have to do is build into it enough simulation of the physics that will make it appear realistic to those who are using it. And when I do that, I have to build a model of that real world. That's an abstraction of the real world right there. And then I'll build into that model enough, I'll build the relationships necessary within the program to support, make that model consistent, basically. And if the model is a good one, then what will happen is that the interactions that the user has with it will tend to, the reactions of the model to their interactions will tend to match their expectations based on physical reality. If the programmer does a bad job, then it doesn't. So you might kick the ball softly and it flies over the bar. And that's sort of not what you expected, because that's not what it should have been, right? For example. But if the model of the physics is right, then you get all kinds of, well, in this case, it's enjoyment, right? It's entertainment. But I mean, this concept I'm describing of modeling physics is not only restricted to gaming. Gaming is one big area. But I mean, when you're trying to predict the weather, that's what's happening as well. When you're trying to predict any physical phenomenon, that's also what's happening.
Well, that actually is a good segue into another question. And that question is, how could the same concept of abstraction be applied to solve big problems like climate change and pandemics, of course, given, I suppose, where we find ourselves today?
Yep. Okay, so let me start with pandemics, just because I have at the tip of my tongue a couple answers, just because, thinking about the situation we're in. One of the ways that abstraction helps is in the modeling of outcomes. So we look at what we're faced with, look at what our governments are faced with as they try to figure out what policies to implement. On one hand, a policy that sort of very closely resembles what we had pre-pandemic is likely to put individuals at risk of catching the disease. And the challenge there is that if too many people need hospitalization, we're going to break the capacity of the healthcare system. So on one hand, you don't want policies that exacerbate the number of hospitalizations that will arise out of people who will inevitably catch that disease. On the other hand, if you are too restrictive, then you will sort of end up starving the economic activity of your country. And so how do you strike the right balance? Now, you can build models for those variables that you care about. So on one hand, you can talk about, there's a classic epidemiological model called the SIR model, which is actually used to study diseases that can only be caught once. So it's not really good for COVID, but it is still used anyway. And as an example, and it's just sort of a mathematical model of how disease might spread. But as an example of an abstraction right there, you're sort of saying, okay, let me focus on the things that I want to pay attention to because they are pertinent to the policy that I'm thinking to implement. So if football wants to come back and the footballers are saying, can we start a league? Can we play? The question should be, and the way that you want to abstract that and model it is, okay, when football resumes, what will change in terms of what are the dynamics of individuals interacting with each other? And what, at the end of the day, I want to make sure I never break the hospital system. So that's my variable I'm going to watch. But what are the other variables I need to pay attention to that will be impacted or affected when more people start moving around in the context of resuming footballing? And that's how you end up modeling that. You look at what are those variables, what are the parameters that I would indicate how the variables are related to each other, and how can we get estimates on them? That's not when you want to actually solve the problem, because what you can then do is you can build models for how these variables interact with each other. You can plug them into simulations and differential equation solvers and what have you. So basically, at that point, once you've abstracted it, you can then compute on it. And those computations then give hints or suggestions as to what would be the likely outcome of various interventions. Now, if we had a data-driven process like that, chances are we'd be striking better balances as we, try and chart our way through this, finding this middle ground between allowing economic activity and not breaking the hospital system. And that's not, I said it as if it's local, but of course this is every government's problem. Every government has this issue. And so that's a very straightforward way that abstraction could be used to address that kind of problem. Climate modeling, also similar. I mean, it's a global scale issue, and the impact is not the same everywhere. And so how you want to model it can depend on abstract it can depend on who you're trying to convince of what. So some people may not care that polar ice caps are melting, but they may very well care that their land is going to be under sea. So, how you go about driving a campaign can also be driven by the right abstractions, meaning you sort of look at what variables you want to represent and use that as the driver, the motivator to get people to act in a way that's consistent with, minimizing the disaster.
Yeah. Okay. And earlier you had spoken about your research as a student and how the growing point language sort of emerged from your initial results, so to speak. So there was a question, and it's asking if you can speak a little bit more about the relationship that exists between abstraction and language design?
So when you're designing a new language, you think in terms of why you're doing it. What is the reason? Who's going to use it and for what? And when you say for what, meaning when you design that language, it often will have embedded in it a particular kind of computation. So in my case, for example, growing point language, its outputs technically are the patterns that were produced, right? So you can think of it as computing these patterns. But when you design a language, its output may not necessarily be that. When I was doing the simulator, its output was the current configuration of the machine. It was responsible for making sure that the mechanical configuration of all the components was exactly as was desired. So in that case, I had a kind of very simplistic, I wouldn't really tout it as a full-blown language, but as a simplistic language that was able, its output is a configuration. And its instructions would basically be very simple commands to change state of computation within particular things. So for example, changing how fast the pneumatic pump was beating, or changing what graphs were displayed on the screen. Those are all different components, and a particular desired state may involve a combination of graphs, a particular rhythm beating, and a particular sequence of flow of fake blood through the heart. So a combination of those things could then be composed within that language. So again, when you're faced with what the challenge is, why are you designing this language? What is the problem you're trying to solve? You then end up identifying what are those, we call them primitive, both primitive data and primitive operations. So what are the fundamental things that you want language to be able to do almost for free, meaning that the person doesn't have to think how it's done, it just gets done. And that would be the primitive procedures. But you also want to think, what are the kinds of things you want to be able to manipulate without having to think too hard about it? That's the primitive data. And then the next component that you have to think about is, what are the means of combination of these things? So you'll have means of combination of data. You'll also have means of combination of operations. That's basically, in our programming language speak, that's like your functions. That's like the ability to sequence, the ability to iterate. Those are means of combination of operations, right? So that's the other component that you think about when you're designing a new language. Once you put all those together, then you basically have your proto language. And the next step, of course, is to try and use it. And if it sucks, then you adjust it so that until it does what you want.
Yeah. So that's, I think, along with the earlier questions, has prompted another question from our audience. And is it safe to say that at the heart of abstraction is the idea of reductionism, and that is fundamental to the scientific mindset?
I don't think so. I mean, reductionism, I think, also entails that the sum of the parts is not greater than the whole is not greater than the sum of parts. And I don't know if I necessarily subscribe to that. Mm-hmm. I think what I would advocate here is that whenever we abstract, whatever it might be, whatever a physical process or a conceptual one, we often leave out details. We often are leaving out things that we don't understand or can't handle. And we approximate them in some way to the point where we're comfortable dealing with that. We see that all the time. You take a system that's a non-linear system, and we say, boy, I don't know how to predict what's going to happen here. You know what? I'm going to focus on this tiny space, and I'm going to linearize it in that space and pretend I was working on a much simpler system, but recognize that it loses validity once I leave that region that I decided to focus on. And so we tend to simplify. And what that really then means is that at the end of the day, the results we're getting out of these abstractions and inferences we draw, we have to be cautious about how much meaning it actually has in the original space that we're working from. So it's important for us to bear in mind that while we're abstracting and enable us to make great strides, but at the end of the day, we never really have the full picture. You know, I mean, a good example is our computers today have billions of transistors all operating in synergy, right? They're working together because we've engineered them that way. We are not focused on what those analog voltages are traveling along those wires and so on. But you better believe that the physical conditions around your computer can have an influence on what those voltages are. You know, you can have a cosmic ray hit your computer and your 0 turns to a 1 somewhere in your computer. So it can happen, and those are things that we do not model within our abstraction. The thing is a 0 or a 1. You know, when I invert the 0, I get a 1. If a cosmic ray hits my thing and it changes it, oops, I did not model that, I can't handle that. So naturally my conclusions will be flawed under those circumstances. So it's important for us to keep that in mind. That's why, and maybe I misunderstand the question. Perhaps if the question was intended to be something different, I apologize, but that's my take on that's how I interpret the question. That's what I take.
And as you said, we in our approach tend to maybe eliminate some of the elements in terms of creating that sort of linear approach or to solving. But we are also at a point where we have accepted that that's not how nature is. And one of the things we've tended to eliminate or have been unable to adequately replicate is probability. And probability exists throughout nature. That is an asset and a factor, a fundamental factor in life. So there is much more to come that will require abstraction, maybe at a different level, so to speak, that has a greater understanding and appreciation of some of these other elements that we have to consider in developing our algorithms, in developing our solutions, to use your examples, relationships, and everything else that comes with it. So it really has been exceedingly informative. And I would love to take some more time. I think we could talk about this and related topics for the rest of the afternoon, but I don't think time will permit us to do so. So I'd like to say on behalf certainly of myself and the audience, thank you so much for spending the past 2 hours or so with us and for sharing your thoughts and ideas and for talking with us about those topics that are of interest to you. It has been really very informative. And I'd also like to, in closing, thank our audience for joining us on the very different platforms that you have decided to. Again, thank you for joining us this afternoon. And I look forward to seeing you all again at our next edition of the Professor Speaks series. So thank you all very much. Stay safe. I hope you have a pleasant weekend. I hope you have a pleasant holiday that's coming up. I don't think we'll be having another one before then. And I look forward to seeing you all again soon.
Well, thank you very much for your attention. It was my pleasure to have given this talk. I hope I have managed to stimulate some thought and some discussion in those circles of audiences that were watching. It is my privilege to have been able to present. Thank you very much.
Thanks again.